So in the last lecture, we learned how to find an estimate for the population based on the sample mean, but we assumed that we knew the standard deviation of the population. Now, we don't always know the standard deviation of the population, right? Because if we knew the standard deviation of the population, then maybe we're also likely to know the mean. So maybe that's not so realistic. So sometimes we do, sometimes we don't. In this lecture, we're going to do this without knowing the standard deviation of the population. Okay, so let's talk about what we do. So instead of using the population standard deviation, we're going to use the sample standard deviation to first estimate the population standard deviation. Then we can use our estimate. So we're still using the sample mean. That doesn't change, okay? But this time we can find the sample standard deviation, and then we're going to use that to help us estimate the population standard deviation. And then everything is essentially the same. So again, this is going to be a lot of repetitive material, but we're not going to use the normal curve, okay? We're not going to use the z-scores. So that's going to be the big difference, but our process is very similar, so don't panic, okay? It's just we're essentially using a different chart. So let's talk about that, okay? So let's first, write down, if we don't know the population standard deviation, we're going to use S, which is the sample standard deviation. We haven't looked at S in a really long time. To estimate the population standard deviation. Okay, now we still need to be able to, we still need the data to either follow a normal distribution or for n to be greater than or equal to 30, because then when n is greater than or equal to 30, then it's approximating a normal distribution. Okay, so that's really important. And notice we've been checking this throughout this unit, throughout confidence intervals. We'll continue to check it in the next lecture, but we also checked it when we were looking at normal distributions in the last unit. So that isn't going to change, okay? Okay, so here's what's different, okay? The sampling distribution is going to follow something called a t distribution, okay? That's the big difference. So originally we used z-scores. Now we're going to find t values, which is the same, but we're using the sample standard deviation instead. So it's a different chart. I will include this chart I'll have it available to you when you do the quiz, and I will include it with these board notes and with this set of videos, okay? So I'm going to write that down so that you don't forget it, and I'm going to put it in another color. And we're going to talk about this t distribution. Okay, so just to be clear, in the past, we have used z-scores when we're using sample standard deviation instead of the population standard deviation. We use t-values. Okay, so let's talk about this. First, let's talk about what a t-value is, right? So t, it's just like a z-score, okay? The only difference is instead of dividing by sigma x bar, okay, we divide it by sx bar. So sx bar is the same thing as sigma x bar. It's s over the square root of n. Now notice here we don't write a mu x bar. That's because mu is equal to mu x bar, so it's not necessary. I'm just going to write this s a little bit more clearly. Sometimes when I write it in the notebook, it doesn't come out as clearly on the screen. So it's exactly like a z-score, right? You're taking the sample mean minus the population mean, and then we're dividing by the standard deviation. So once again, we're looking for how far are we, okay? How many t-values are we away from the mean, okay? Very similar to the z-score. Now, why is that? The reason why that occurs is because the t-distribution is very similar to the normal curve, the normal distribution, okay? So, and I'll put that down here, but I'm going to give you all of the properties of the t-distribution. Okay, so once again, let's stick this in a different color because this is important in order to understand what's going on. So these are the properties of a t-distribution. Okay, and there are a lot of them, but so many of them are just comparing it to the normal curve. So for example, the mean, median, and mode are equal to 0. This is just like a normal distribution. And I'll draw a diagram once we go through all of these properties. But if you remember, okay, if you remember, the mean, median, and mode are at 0, and then the z-scores are measured as 1 standard deviation away from the mean, either above or below, 2 standard deviations, either above or below. That's how we figure out those z-scores, right? How many standard deviations are we away from the mean, the median, and mode? But when we graph that normal curve, the mean, median, and mode are located at 0. Right? The z-score is 0 because we are 0 standard deviations away from the mean. So this is essentially the same thing. The mean, median, and mode are all the same, and they're all located at 0. Okay? The other thing that's similar to the normal distribution is that the curve is bell-shaped. Just like the normal distribution. And it's symmetrical about the mean. Also, just like the normal distribution, okay? The total area under the curve is equal to 1. Again, just like the normal distribution. Now here are where the differences start, okay? The tails are thicker than those of the normal distribution. So they come up higher, and when I draw the diagram, you're going to see what we mean by that. So in the tails for the normal distribution, the area under the tail gets closer and closer to 0. Here, it gets smaller and smaller as you get further away from the mean, but it comes up higher. It's not as close to 0 as it is for the normal distribution. This is another one. The standard deviation is going to vary with the sample size. And it's always greater than 1. Two more. Okay. The second one, again, you'll probably need the diagram in order to completely understand it. But essentially, the t-distribution is a family of curves. So it's not just one curve. Normal distribution is one uniform curve. No matter what the sample mean is, or the population mean, no matter what the standard deviation is, it's one curve. The t-distribution is multiple curves. Which curve it is going to change what the t value is, right? The z-score is always the same. We go to that table, the z-score for 1.65 is always the same, okay? The area under the curve for any z-score is the same. For the t values, that's not true because you have lots of different curves. So the area under a curve at a specific t value, right? If we go to a chart, we have a t chart, okay, chart for the t distributions. And if we go to the t chart, there's something else that will also determine the area. So that area will change. Okay, it's not the same regardless of X bar and S. Okay, it will change again because it's a family of different curves. And what's going to determine it is something called a degree of freedom. And again, we'll talk about this in more depth. So what is the degree of freedom? The degree of freedom is the number of free choices left after a sample statistic such as the mean is determined. So I'm going to define that later because it needs a lot more discussion, okay? So the last thing is, as the degree of freedom increases, the t-distribution gets closer to the normal distribution. Okay, so I'm going to draw you a diagram, but I admit that my diagram might not be the best diagram because to draw it in a symmetrical way so that it looks correct may not be perfect. I want it in the board notes though, so that's why I'm going to draw it, but I'm also going to show you a better diagram that's a little bit more accurate. Okay, so for example, let's draw the standard normal curve. So suppose remember we said our standard normal curve is very close to it comes down very close, right? Our tails get closer and closer to zero. So this is our standard normal curve. Okay, now we said that a t-distribution is based on something called the degrees of freedom. Okay, and again, we'll talk about this more, but we also said it's a family of curves. So there are lots of different types of curves in a t-distribution. So let's talk about, I'm going to draw you those examples. Okay, so suppose that our degree of freedom is 2. So first of all, we'll put this here. This is our 0, right? This is our mean. Okay. Now, if our degree of freedom is 2, then our tails are higher. Okay. And it doesn't come up as high as the standard normal curve. So again, this may not look completely symmetrical, but I'll do my best. Okay, this would be a t-distribution. Degree of freedom, we abbreviate as DF. Okay, sorry, that really doesn't look good. Like I said, I'll give you a nicer diagram. Okay. If our degree of freedom is higher, okay, so remember what we said it as the last thing, as the degree of freedom increases, the t-distribution is going to approach the standard normal distribution. So if we change, let me change this color and do a higher degree of freedom. We'll do this one in green. So if our with a higher degree of freedom, the tails are gonna go lower because they have to approach the normal curve. And its peak gets higher. Hopefully that's clear from this. This is a t distribution. With a degree of freedom that's equal to 5. Okay, so you can see that here the tail gets lower because it approaches the normal distribution, and the peak gets higher, again, because it's getting closer and closer to what the normal distribution looks like. Okay, what does this actually look like? Here's a nicer example. So you could see that if the normal curve, okay, this uses a degree of freedom of 13 instead of 3. So it does 5 and 13. It doesn't really matter because it's what you're looking for is the fact that it's getting closer and closer to what the normal curve looks like. So your standard normal curve, okay, t with degree of freedom of infinity, okay, because as it gets higher, it gets closer and closer. Your standard normal curve is in this nice light color, okay? Then you have a t distribution with a degree of freedom of 5. So the tail is going to come up higher, okay? And the peak is going to be down here. Tail comes up higher. When the degree of freedom is 13, so the degree of freedom is increasing, the tail gets lower. So as the degree of freedom increases, the tails are going to get lower. So when I talk about tails being higher and lower, that's what we mean by thicker, okay? So this tail is thicker than the normal curve. It doesn't come down quite as fast, okay? So the tail gets lower for the degree of freedom of 13, and the peak gets higher because it's approaching the normal curve. So the normal curve is like the highest t, the highest degree of freedom that could exist, okay? And the tails are the lowest, okay? They're let me restate. When the degree of freedom gets really high, the peak increases and the tails decrease, okay? The tails get thinner and the peak gets higher, right? Tails get thinner and the peak gets higher because in the standard normal curve, that's when you have the thinnest tails and the highest peak, okay? And what you can see with these different degrees of freedom is exactly that as the degree of freedom increases, the peak will increase and the tails will get thinner. So degree of freedom of 5, here's the tail. So if you look at the same point on the curve, so like over here, let's say, looking at the same point on that curve, the tail for a degree of freedom of 5 is higher than the tail of the degree of freedom for 13, okay? The peak is the opposite. The peak is higher for the degree of 13, and it's lower for the degree of freedom of 5, okay? So let's just write that down, what we mean by this degree of freedom. So first, with respect to the curve, as the degree of freedom increases, the peak gets higher, and the tails get thinner. So what are we saying? The curve looks more and more like a normal distribution, which is what the 7th property was. Okay, so before we go into detail on those degrees of freedom, let's just compare the curves one more time, Okay, compare the properties one more time while looking at the curve. So the first thing is that the mean, the median, and the mode are 0. So hopefully you could see it here. You could get the basic idea that here's the 0. This is a t-value of 0. This is where your mean is located, exactly in the center. The curve is bell-shaped and symmetrical about the mean. Hopefully you could see that. That's the same as the standard normal curve, which is the one in blue. The total area under the curve is 1. So when we talk about the total area, that's if we shade in everything under the curve, we would say that that's equal to 1. Okay. The tails are thicker than that of the normal distribution. So you could see that the tails, even for a degree of freedom of 5, they come up higher than the blue curve. The standard deviation will vary with the sample size. Okay, and it's always greater than 1. So that's something that you're going to see not with this. You're going to see it when we get into more depth with this whole thing. And it's a family of curves. So you can see that you have lots of different curves, right? Depending upon that degree of freedom, which we'll talk about. If the degree of freedom is 2, it's a different looking curve than if the degree of freedom is 5. That's going to be a different looking curve than if the degree of freedom is 13. Okay. And as the degree of freedom increases, the t-distribution is going to look closer and closer to the standard normal curve. So that's essentially the properties. What we're doing in the properties is we're describing what this curve looks like. Okay. Degree of freedom. In order to understand all of this, we have to understand what a degree of freedom is. So let's talk about that. So we're going to define it, and then we're going to talk about it a little bit. And then we're going to start doing exactly what we did in the last lecture. So what is a degree of freedom? That did not come out right. That still did not come out right. Sorry about that. Okay. So I'm going to give you the exact definition, and then I'm going to explain the definition. Okay. So this is the number of free choices left after a sample statistic such as the mean is determined. Now it turns out that there's an answer here, okay? That you can figure this out very easily. So if you are using the sample mean to estimate the population mean, which is what we're doing, remember the sample mean is being used as a point estimate for the population mean, and then we're developing confidence intervals, just like we did in the last lecture. Then the degree of freedom. And again, we abbreviate this as DF is equal to N minus 1. And remember, N is the number of, N is your sample size. Okay, so no matter what, if you are trying to find the degree of freedom, it's the sample size minus 1. Okay? Okay, so what do we mean by number of free choices left? Okay, let's go through an example. Okay. So we're asking ourselves, why do we subtract 1 from the sample size? To get the degree of freedom. That's the question that we're asking, which is the same thing as, what do we mean by the number of free choices? Okay. Okay. The degree of freedom is the number of values that are free to vary. And we're going to explain this as well. Okay. And I really should change all of this to degrees of freedom. Okay. So what does this mean? Okay. Degree of freedom is the number of values that are free to vary. What does that mean? Let's take an example. Okay. So suppose that we have a set of numbers with a mean of 10. Okay. What are some sets that we might pick? Okay. We could have 9, 10, and 11. This has a mean of 10. But there are other sets of numbers that also have a mean of 10. 8, 10, 12. That has a mean of 10. 5, 10, 15. That has a mean of 10. Okay. Okay. Once you have chosen the first two numbers, if we take two numbers, once we've chosen the first two, like if we chose 9 and 10, the third number is fixed. There is only, of the third number, there is only one number that you can choose that'll give you a mean of 10. Okay, so if you pick three numbers with a mean of 10, after you've chosen the first two, you have no choice in the other numbers. Saying three numbers with an X bar of 10, once you choose the first two, There is no choice for the third. What does this mean? If we choose nine and 10 as the first two numbers, I'll write it as 9 and 10. "11 must be the third number." We have no choice in the matter, okay? So once you've chosen the first two numbers, okay, the third number is fixed. What does this mean? We only have two numbers that can vary, okay? Only two numbers can vary. We could choose 9 and 10, we could choose 8 and 10, we could choose 5 and 10, we could choose 10 and 12, we can choose 10 and 15, but we can't, once we have those first two numbers, we have to have one number as the third number. The third number is fixed, okay? So this means only the first two numbers can vary. Now I underline that because we said, okay, we just said that the degrees of freedom is the same thing as the number of values that are free to vary. So this is saying we are free to choose the first two numbers as whatever we want, but we're really not choosing the third, okay? So we are free to choose the first two numbers but the third number is fixed. Now this is true regardless of the number of numbers that we choose. So for example, if we are choosing 10 numbers instead, or I'll make it a different number so it's different from the mean. If we're choosing 7 numbers with the mean of 10, we are free to choose the first 6 numbers as whatever we want. But the 7th number is fixed. Okay, I want you to notice that the 6 numbers is n minus 1. Okay, so the first 6 numbers could be 1, 2, 3, 4, 5, 6. The 7th number has to be a specific number so that we get to a mean of 10. Okay, we could choose the first 6 numbers to be 2, 4, 6, 8, 10, 12. The last number, there is a specific number to make the mean equal to 10. We can't choose all 7 numbers because then how do we guarantee that the mean is 10? But the first 6 we can choose to be whatever. Doesn't matter. I could say give me 6 random numbers and I'll tell you what the 7th number is. That's a formula that we can develop, okay? Because we know that the sum of the numbers has to be the sample size times 10, okay, right? Sum of the numbers over the number of numbers is equal to the mean. We know that because that's how we find mean. So the first 6 numbers are completely up to you. The 7th number has to be fixed. So that's why we say that the degree of freedom is n minus 1, okay? That's what we're doing. Okay. So now that we understand what a t-distribution is and the fact that it's based on, t-distribution is because it's based on the sample mean instead of the population mean. That's why we're using a t-distribution, okay? And we're using the t-distribution to approximate the normal distribution, okay? And again, it's because we do not know the population standard deviation, okay? All of this assumes that the distribution of the random variable is approximately normal. What does that mean? The data follows a normal distribution, or n is greater than or equal to 30, okay? So now let's do some calculations. So we're going to do the same thing here, okay? We'll put this in red because I want you to see that we're moving on. The whole first part of this lecture is just describing what is a t-distribution. Second part of this lecture is using the t-distribution to approximate the population, to create a confidence interval for the mean. So again, what's the difference? How do we know when to use a t-distribution versus a normal distribution? Okay, in other words, we'll call it a t-value versus a z-score. Our sigma is unknown. Okay? Okay. So right now, all we're going to do is just like we started using the z-score table to find the z-score. Now we're just going to learn how to use the t-chart in order to find the t-value. Okay? So we're just going to do some exercises with the chart, using how to use the chart, and then we can move on to these actual calculations, which is similar to the calculations that we did in the last lecture. So we're going to start with we call it the critical value for t. This is t sub c. It's similar to z sub c. Okay, it's the area under the curve. It's the exact same thing that we found with z sub c. It's just using the t-distribution. Okay, now the difference is that we need to know the confidence interval and we need to know the sample size. Okay, so we're going to specify that. So for a 95% confidence level, so for a z-score, you needed to know the confidence level too, right? In order to figure out the area under the curve for the z-score, we needed to know the confidence level, because the confidence level is the area under the curve. I'm going to put based on up here. That's more accurate. Okay. For a 95% confidence interval, when n equals 15. And the reason why we need to know the sample size is because the t-distribution, right, is a family of curves. So we have to know which curve we're dealing with. So this is the area under the curve, just like it told us the area under the curve for the z-score. This will tell us the degrees of freedom, so we know which curve we're working with. That's why we need the sample size. Okay, so just to summarize one more time. Okay, we're using a t-distribution. Why are we using a t-distribution? Because we don't know sigma. What do we need to do? We need to find our critical value for t. Okay, why do we need to find that? We have to know how many standard deviations away from the mean we are. This is just like finding the critical value for z. We have to find the area under the curve. The area under the curve is going to tell us the t-value. What tells us the area under the curve? The 95% confidence interval tells us what the area is. Okay? We need to find the corresponding t-value, just like we needed to find the corresponding z-score. The difference is that we have to know which curve we're dealing with, because the t-distribution has many, many different curves. For the z-score, it was only one curve. It was only the standard normal curve. So we need an extra piece of information. We need to know what the sample size is. The sample size tells us the degree of freedom. Okay, so we're going to do exactly the same thing, and then I'm going to show you what the curve looks like, what the t-chart looks like. And actually, it's a lot easier to use because you don't have to do any calculations, right? For the z-score, we needed to figure out, well, 95% is the area within the interval. Okay, we needed to figure out what the area outside the interval was. So we had to do that 1 minus 0.95, then divide that by 2. We don't have to do that here. Okay, the t-chart gives that to us. The only thing that we need to do is calculate the degree of freedom. But we already know what that is. That's n minus 1, always. It's always n minus 1, because we can always choose the first n minus 1 numbers, and then the last number is fixed. Okay, so the degree of freedom here is 15 minus 1, or 14. Okay, let's look at this t-chart, okay? So C is your critical value. Okay, it's just like in the last lecture, right? We said what C was equal to. Our critical value is 90, our confidence interval. I'm sorry, not your critical value. Confidence interval. Okay, so your C is 0.95, so we don't have to do the 1 minus C and then divide that by 2. We don't have to do that. Let's go to our t-chart and see what it looks like. Okay, here's our C-chart. Looks so complicated, right? It's not complicated, okay? Not at all. So all we have to do is look at our C and look at our degree of freedom, okay? So this is just saying what the area is. So let's just talk about what this 1 tail, 2 tails is, okay? So this is saying that the area in the middle over here is 80%. This is 80% of the area under the curve. Then the one tail versus two tail is saying, well, if the area under the curve is 80, the area in the interval is 80%, then the area remaining under both tails is 20%, and under one tail, it's only 10%. This one is saying the area in the interval is 90%. Okay, notice your interval goes from negative t to t. I don't know if that's hard to see here. Okay, I'll magnify it. Your area here goes from negative t to t. Okay, so the 0.9 says 90% is in between here. Under two tails, you see 0.10. So that 0.10 is saying, okay, the remaining 10% is under the two tails. And then for the one tail is 0.05. So that's saying 5% of the area is under one tail. For the 95, the 0.95, same thing. 95% of the area is in the middle. Under the remaining two tails is the remaining 5%, which means under one tail is just 0.025, okay, or 2.5%. This one says 98% is within the interval, which means 2% is under both tails. That's why it says two tails, 2%, which means under the remaining tail is just 1%. This one talks about 99% of the area being within the interval, which means under the two tails outside the interval is 1%. And if we just look under a single tail, which is what we want here, then we have 0.5%. Okay, so this is just telling you what's going on with the areas, okay? But you don't have to actually do any calculations. For the z-score, we had to calculate this. For the z-score, we had to calculate what was under one tail. And we used this number and went to the z-score chart in order to figure out what the z-score was for that area. Okay, here we don't have to do those extra calculations. You see, it has 80% and it does the calculations for you in the t-chart. Okay, so you're going to look at two things for this t-chart. You're going to look at the confidence level and you're going to look at the degree of freedom. So our confidence level for this is 0.95 and our degree of freedom is 14. So if we go to the 0.95 column, and we look at the row that says 14, we get 2.145. So that's our critical value for T, 2.145. How did we get this? We got it from the t-chart. Okay, let's do another one. This time we're going to do it for 90% confidence level. And we're going to say when n equals 22. Okay, so I'll put our answers in pink. We have to find the degree of freedom. The degree of freedom is 22 minus 1, right? It's our n minus 1. So our degree of freedom is 21. Our C is given to us. It'll always be given to us where it'll say, hey, you make up your mind. You figure it out. And if it says you make up your mind, then that's literally what you're doing. You're making it up, okay? You're not doing any calculations. You're saying, well, I want to be 90% confident, or I want to be 98% confident. You're making it up. Otherwise, it's being given to you, okay? Sample size is given to you. So we just take the sample size and we subtract 1. We take the confidence interval and we turn it into a decimal. And then we go to our t-chart My t-chart is over here. We go to our t-chart and we say, okay, well now we're looking at the 0.90 column. And we're going to go all the way down to 21, because 21 is our degrees of freedom. So if we go to 21, that's our row. Our column is 0.90. So our t-value is 1.721. Okay, let's do another one. We'll do one more. Because we're going to do a lot of these when we're actually doing our calculations. This is just to help you get used to the chart, okay? So now we're going to find our t-value for, let's do 98% confidence interval. And we'll say that our sample size is 10. So once again, what do we need to do? We need to find our degree of freedom. So we're doing 10 minus 1, which is 9. Our C is given to us. We just turn it into a decimal. It's 0.98. So our T sub C, we go to the chart. Try and do this on your own first. So you might want to pause the tape and do it by yourself. Okay. So it's a 98% confidence level. So we go up here. So you're looking at this C, level of confidence, 98% confidence level. And our degree of freedom was 9. So we go down to the 9th row and we get 2.821. Okay, notice it's much easier to use this chart. We don't have to go looking at lots and lots of numbers. The z-score chart is much, much bigger. And we have to go and look inside of here for the numbers. We don't have to do this with this one. Okay, this is different. Okay, so let's actually use this. So there is nothing here that is different, okay? There's nothing here that is different. The only difference is just what we're calling these values. So what are we calling these values? Instead of a z-score, we're calling it a t-value. Instead of using the population standard deviation, we're using the sample standard deviation, okay? So now let's find our confidence interval. It's the exact same process as the last lecture. Okay, so the first thing is you're going to determine your point estimate. I'm going to put it in the exact same order as we did before because it's the exact same thing. Okay, I should be... So you're determining your point estimate. So it's the same thing here. So the point estimate for mu is x bar. That didn't change. Okay, that's exactly the same thing. And you don't have to, you're just kind of identifying it, okay? Because that's what's going to give you your interval, right? The second thing that you're going to do is you're going to check that the data is normally distributed. You could actually do this first, because if it's not, normally distributed or n is not greater than or equal to 30, then you stop. You can't do anything, right? So you're going to check that the data is normally distributed or that n is greater than or equal to 30. Same thing as the last lecture and the last unit. Okay. Then you're going to determine your level of confidence. Again, this is given to you or you're just making a decision. Then you're going to find T of C. Just like we just did. So based on your C and your degree of freedom, which is equal to n minus 1, right? That's what you need. So no calculations. The only calculation that you're doing is n minus 1. Then you're going to find your margin of error. So your margin of error you calculate in the same way. The only difference is that instead of sigma, you're using S. Okay? Sorry, that should not be an equal sign. So it's times x square root of n instead of sigma over square root of n. Okay? And the last thing is you're going to use E to find the interval. And this is exactly the same thing as before. Okay. You're going to do your sample mean plus your margin of error and your sample mean minus your margin of error. That's it. Okay. So let's just do some examples of this. So again, the only difference between this and what we did in the last lecture is that instead of finding Z sub C, you're finding T sub C. You're going to the T value chart instead of the Z score chart. Okay? That's the only difference. So example, we randomly select "16 coffee shops. And measure the temperature of the coffee. The temperatures are normally distributed with X bar equal to 162 degrees Fahrenheit. Okay? And your sample standard deviation is 10 degrees Fahrenheit. We want to construct a 95% confidence interval. For our population mean. Okay? So again, remember, and this is a repeat from the previous lecture, right? When we take a sample mean, it's very unlikely that it's the actual population mean. It might be really close, but it's not the actual population mean. So we're saying that there's a 95% chance that the mean for the population falls within this interval, and that interval is based on the sample mean, okay? And it's based on what that confidence interval, what confidence we want to have in that interval, okay? So let's calculate, okay? So we're going to go through each of these 5 steps. So what's our point estimate? This is not really a step that you have to write. I'm putting it in here. Okay, so we're saying that our mu is somewhere on both sides of that 162. I don't think that we actually put this as a step. I just want you to be clear that we're saying the population mean is, we're estimating it to be 162, but we know it's not exactly 162. It's got to be a little bit more or a little bit less, okay? Is the data normally distributed? Yeah, it is normally distributed. So we don't care about our n. Our level of confidence is 0.95 that we get from this 95% confidence interval. So now we can find our T sub C, okay? So our degrees of freedom that we need to actually say is, it's 16 coffee shops, so it's n minus 1, which is equal to 16 minus 1, or 15. So now we know what our C is, we know what our degree of freedom is. We go to our T-chart. Here's our T-chart. We're looking at degree of freedom 15, and we're looking at the column that says 95%. So it's 2.131. Then we have to find our margin of error. So our margin of error is our T sub C times our standard deviation over the square root of n. So our T sub C is 2.131. Our standard deviation was 10, and our n was 16. So this is 5.3. Now we're going to construct our interval. So we're going to do 162 plus 5.3, which gives us 167.3. Then we're going to do 162 minus 5.3. And that gives us 156.7. So what are we saying? We're saying that the population mean falls somewhere between 156.7 and 167.3. Okay, so the mean temperature of the coffee is somewhere between these two numbers, with 95, there's the probability that it's somewhere between those two numbers is 95%, okay? This is the typical confidence interval, by the way. That's why we've been using it so much, because most confidence intervals are 95%. You can always get more higher percent if you want, okay? But this is the most typical. Okay, let's do the same thing, but this time with a confidence interval of 90% and a confidence interval of 99%. Okay. So same data. I want you to think about what's going to change. Our point estimate is always the same here. The level of confidence, is that changing? Sure, it's changing because we're constructing a different confidence interval, okay? If the confidence interval is changing, then the t-value has to change. But the way that we find the margin of error isn't changing, okay? The degrees of freedom isn't changing because the sample is the same, okay? So the interval changes. I want you to think about one more time, is the interval going to get larger or smaller if it's a 90% confidence interval, okay? I encourage you to do this on your own first. So pause the tape, try it on your own, see if you get the same thing, okay? So for this one, first thing that we're going to do that's different is find the degrees, find the t-value. T-value is different because our C is now 90%. So if we go to our t-chart, again, the t-chart is given to you. You go to 0.90 and our degrees, our sample size is still 16. So we still go to a degree of freedom of 15. So now the difference is that our t-value is 1.753. And if our t-value is 1.753, then we're going to plug that into the margin of error instead. So times 10 over the square root of 16. And if we calculate that, we get 4.3825. Okay, and this is something that I would really practice, is putting it into your calculators, okay? Because that's where I could see careless mistakes being made. So what do? Now we construct our interval. So x bar plus E says we take 162 plus 4.3825, which gives us 166.3825. I would be okay with your rounding to the nearest hundredth. So if you put 166.38, that would be okay. Now we do the same thing, but we subtract the margin of error. And again, if you round to the nearest hundredth, that's okay. So the 162 minus 4.3825, and we get 157.6175. So what's our interval? 157.6175, or if you wrote it as 157.62, I would still give you full credit, but you shouldn't round more than the nearest hundredth, okay? And you're asking yourself, does this make sense that the interval is increasing, decreasing here? And we asked this question the last time too, right? We said, if the confidence increases, if the confidence decreases, what's going to have to happen to the interval? And we said as the confidence decreases, the interval is going to get smaller, okay? Which makes sense. It does make sense, right? So just like we said last time, if we say, okay, well, the sample mean is 162, we're pretty confident that the population mean is going to be between 100 and 200, okay? But we're going to be less confident that it's between 150 and 180, okay? As that gets closer and closer, we're closing the interval. So as we decrease the interval, the confidence level is going to decrease. Because you're leaving less room for error. Let's do one more with this set of data, and then we're going to do one with a different set of data, and that'll be it for this lecture. Okay, so let's use the same data just so that you could see the difference. Okay, this one, our interval got smaller, not much smaller, but it got a little bit smaller, right? Here, let's use the same data again. But this one, we're going to do 99%. So again, this isn't a lot of work, right? There's not all that much that we're doing. Our C is equal to 0.99 now. Our degrees of freedom hasn't changed, right? It's still 15 because our sample size hasn't changed. So we could go directly to our t-charts. And when we go to our t-chart, we're still at row 15, but this time we're going all the way to 0.99. Okay, notice the area under the curve increases. That's because the area outside the 99%, the area outside the 99% is decreasing. So our t-value is increasing. So 2.947. Now it's just a plug and chug. I did that right. Sorry, I was just double checking it. So our E is 2.947 times 10 over the square root of 16. Which gives us 7.3675. So now we construct our interval. So we do our sample mean plus our margin of error. Which gives us 169. I'm again okay if you rounded this to 7.37. This I wrote wrong. 169.3675, and then an x bar minus our margin of error, which is 162 minus 7.3675. Which is 154.6325. And notice our interval got bigger. And we said that you can see that even visually. That if the area under the curve is increasing, then that interval from negative t to t has to get bigger. Let's do one more, but with different data, just that you could get accustomed. So suppose that we're selecting $36 cars. At a used car dealership. And we determine the number of days that they've been sitting in the lot. Before being sold. Okay. The sample mean is 9.75. The sample standard deviation is 2.39. Okay, and we want to construct a 99% confidence interval. Okay, what do we have to do? Well, we know what the point estimate is, right? The point estimate is the sample mean. But we have to do that check first, right? N is greater than or equal to 30. So it doesn't matter if the data is normally distributed. You have to check for this. Once again, if this is not true, if N is less than 30 and it's not normally distributed, then you stop. You cannot do anything. The reason why it's okay if N is greater than or equal to 30 is because as N gets larger and larger, it's closer and closer to a normal distribution. So once we check for that, our next goal is to find our t-value, okay? So in order to find the t-value, we need to know our c. Our c is given to us as 0.99. And we need to know the degrees of freedom, which is n minus 1. Again, the degree of freedom tells us which t-curve we're dealing with, okay? So 36 minus 1 is 35. So now we go to our t-chart and we say, okay, on the t-chart, we're going to go to row 35 and we're going to go to the 0.99 column, which is 2.724. Now we just plug that into our margin of error. This is really the first calculation that we're doing, and it's really the only calculation that we're doing. So 2.724 times 2.39, because that was the sample standard deviation, over the square root of 36. And we get 1.09. Okay, now we find our interval. So I'm going to do it up here. X bar plus RE is, X bar is 9.75. So 9.75 plus 1.09. is 10.84. And an X bar minus our margin of error, so 9.75 minus 1.09 gives us 8.66. So what is our interval? It's between 8.66 and 10.84. Okay. So let's just summarize. When do we use the normal distribution versus the t-distribution? Okay. When we say normal distribution, what we're saying is, when do we use the z-scores versus the t-distribution, which is clearly t-values. Okay, well first, if it's not normally distributed and n is not greater than or equal to 30, you can't use either. So if n is less than 30, or the data is not normally distributed, you can't use either. If sigma is known, you use z-scores. If sigma is unknown, I wrote known. I meant unknown. Use t-values. And that's it, okay? It's exactly the same thing that we did in the last lecture. It's just that, one, we introduced you to what a t-distribution is, okay? And two, if you're using s instead of sigma, okay, then you use the t-values. If you're using sigma instead of s, then you're using the z-scores. That's the only difference between these two, okay? Otherwise, our calculations are the same. It's just which chart are you using. And that is it. It will take me a second to stop the tape, so stop listening right now.